Okay, in this video we're going to continue exploring the connection between a second order differential equation of this form and the corresponding linear system. We've seen that they have basically the same characteristic polynomial, same characteristic equation. What I want to do is look at the third possibility. We've looked so far at what if there are two distinct real roots, what if there are complex roots. Now I want to say what if there's only one real root and it's a repeated root. So here I'll call that S1, here I'll call it lambda 1. Now, when we have a linear system like this, and we have one real eigenvalue, we saw that there were two possibilities for that. It could be that we'd find two independent eigenvectors, and that meant that every solution other than the equilibrium solution was a straight line solution. Every vector other than the zero vector would be an eigenvector. Turns out that's not possible for a system like this that corresponds to a second order differential equation. And let me just show you why. If that were the case, then I would know that y prime v prime was just lambda times yv. Because if this was the zero vector, that's always true. Okay? And if it's not the zero vector, it would be an eigenvector. So that would tell me that y prime was equal to lambda y. But I've got that y prime has to equal v, and that's a different relationship. Now, there may be some values of y and v for which both relationships could be satisfied, for which v would actually equal lambda times y. But remember, we've seen that systems like this satisfy the existence and uniqueness theorem, so for any arbitrary initial condition that I have, there's got to be a solution that passes through that point. And not every pair of values is going to satisfy this equation. So, if we have a linear system that corresponds to a second order differential equation like this, and there's only one root for the characteristic equation, it's going to be the case that we have only one independent eigenvector, and therefore we know that our general solution here is going to be e to the lambda 1 t times v naught plus t e to the lambda 1 t times v1, where remember v naught was the vector consisting of our initial condition, and then v1 is determined by that, because v1 was a minus lambda I times v naught. Okay. So I want to just take a look at what that means that's going to look like. So I'm going to call v naught, I'm just going to call that y naught v naught. Okay. And for v1, let's call that y1 v1. So what we're getting then is yv is equal to e to the lambda 1 t times y naught v naught plus t e to the lambda 1 t times y1 v1. Okay. Now, if I'm trying to solve this, I'm just looking for y. Of course, once I know y, if I wanted to know v, I would just take its derivative and then I would have v. Okay. If I take a look here at what just the y value is then, my y is e to the lambda 1 t times y naught plus t e to the lambda 1 t times y1. So it looks like we're getting a linear combination of some e to the lambda 1 t's and some t e to the lambda 1 t's. Now I know that is an arbitrary number because remember v naught was just y naught v naught. That was my initial condition. So these were really the two arbitrary constants that we had in this system. And then we said these two constants we would get by multiplying a minus lambda I times this thing. Okay. So y1 is determined. But y1 is determined by what y naught and v naught are. And v naught doesn't show up anywhere here. Okay. So when I'm working with this system, I say, oh, pick an initial condition. Great, that will determine this vector. If I'm just solving for y, I can actually view y naught and y1 as both representing arbitrary constants. What I would have to do if I wanted a particular y1 here, I would just have to rig it, so I would have to pick the v naught that would give me the y1 that I wanted here. Okay. But that means we can translate this back to our second order differential equation so that the general solution here will just be, I'm going to change the names of the constants. I'm going to go with a copies of e to the s1t plus b copies of t e to the s1t. Okay. So, and similar to what we have over here, we are not assuming that that is a solution and that is a solution, and we're taking an arbitrary linear combination of them. Same thing here. I am not supposing that that is a solution and that is a solution. I'm saying that when I put them together, that gives me the general solution for a second order differential equation of this form.